plan to be in my office on the days before class, normally at least an hour or so before the class. So if you want to come by and chat about what's going on, any questions, technical, philosophical, anything you want, that's probably a good time to find me and talk. Still not starting. Is there a light on? There's a light on there? Up here somewhere? This thing that says off? No? Aha. Is that what you want? That's sort of mood lighting. I mean, I'm not sure exactly what you think is happening in this class. But I think we did precisely nothing, right? No, is it better now? Okay, cool, great, excellent. Very good. Okie dokie. So today we're going to learn how to calculate lots and lots of amplitudes. So we're going to talk about BCFW recursion relations and maximal SUSY. And as I've said a number of times, we're going to begin to see some more unusual and sort of magical ideas starting to show up. OK, so now what I showed you last time is that if someone hands you some collection of amplitudes, let's say tree amplitudes, then you can check all by your lonesome without calculating all the Feynman diagrams, whether it's right or wrong, by, for example, checking if it factorizes correctly on all the poles. And we looked at the Parke-Taylor amplitudes and verified that the Parke-Taylor amplitudes do indeed factorize on the poles in that way. So today we're going to start trying to be more proactive about computing amplitudes and saying, look, we know we have a function. It's a rational function of a bunch of momenta, lambdas and lambda tildes. We know a lot about where its poles are. Why can't we completely determine it? I mean, after all, you're familiar with this in complex analysis, that if you have a rational function of one variable, then it's almost entirely determined by knowing its poles. So let me remind you how this works. Just a consequence of Cauchy's theorem is that, let's say you have a function f of z, OK? And let's say I know that, or let me call it f of w. And let's say I know that f of w goes to 0 as w goes to infinity. This isn't strictly necessary. It just has to have no pole at infinity. But anyway, let's be simple and just say that f of w goes to 0 as w goes to infinity. Then I can compute f by the knowledge. And if I know that it only has poles somewhere in the complex plane at some various locations, then I know that I can just immediately write down a formula, right? I can say that f of w is the sum over all the poles, some residues Ri divided by z minus w minus, let's say these locations are wi, w minus wi. And Ri is just the residue of f on the pole. OK? And one of many ways of deriving that is to do a Cauchy integral. So I can consider a new function. Let me call it little f of z, which is my big F of w plus z. OK? Now, this is slightly different now. Now in z space, little f has a bunch of poles inherited from the poles of capital F. But now I can look at this object. I can look at the contour integral around z equals 0 of f of z, little f of z. On the one hand, that's equal to f of 0. But on the other hand, I can deform the contour and wrap it around infinity. And instead, I get negative the sum of all the residues of f at I over z minus where the poles are. And again, the poles in z are just when w plus z equals wi. So when I shove this back, not z minus zi. This is just the residue of fi over zi. Okay, and the poles of capital F are exactly when w plus z is equal to wi. Okay, so zi is exactly equal to wi minus w. And so that's exactly the formula that we talked about the other way. Okay, so that's just telling you that if you have a function that vanishes at infinity and you know this residue is on all the poles, then you know what it is. And there are many ways of, there are many equivalent words for this. This is, for example, the same as partial fractions. Okay, so you have a big expression, you imagine combining everything under a giant denominator, then this is a way of breaking it up into individual pieces, each piece that has one pole at a time. Okay, now, so this is very familiar, and we'd like to, conceptually, we'd like to do the same thing for amplitudes, except now the amplitudes look a little more complicated. They're functions of many, many variables. Okay, and so they have poles in lots of complicated places, a function of many, many variables. So what should we do? Well, we should do just what we did here. See, in this example, we had our actual function f of w. We wanted to expand f of w in some way, as summing over poles. And the way to think about it is to explore this function of, in this case, one variable w by a one variable deformation z. Okay, in this case, 1 equals 1, so we don't seem to be buying much. But we're now going to do the same thing for amplitudes. Okay, so instead of thinking about the amplitudes as a function of momenta for all possible complex values of momenta, we're going to do something else. We're going to freeze the momenta, most of them, and then we're going to explore momentum space in a one-dimensional direction. The simplest possible way to sort of complexify the momenta. Okay? Now, what's the simplest thing you would do? Well, the simplest thing you could do is to say, let's do this in general, any number of dimensions. So I have some amplitude. It depends on n momenta. And let's say I want to take some momentum I, and I want to go off in some in the complex plane. I want to complexify that momentum. Well, so I'm going to add plus some z q mu to it, right? I'm going to choose some q, and I'm going to go off in the direction of z. Now I have a function of z. There's only one small problem. What is the small problem? Why can't I literally do this? See, if it was me, I would have stopped at this point. That's why I'm not BCF or W. Brito, Cacciazzo, Feng, and Witten. And Ruth Brito was Andy's student, and Freddie Cacciazzo was Cumrun's student here. And they did this work very shortly after they started their postdocs. OK, so anyway, I would have stopped and said, so I can't do it. So what should you do? Sorry, what is the problem with this? Yes? We'll come to that in a second. There's a worse problem with it. We bet momentum conservation. OK? So what should we do? We add something to one momentum. So what's the dumbest thing that we can do next? We can subtract the same thing from another momentum. Okay, so we have to touch two variables. Let's call it pi and pj. We're going to take pj goes to pj mu minus zq mu. Okay, so now at least momentum is conserved. Good. Step 2. Now we come to your other complaint. We have to make sure that this guy is null. Right? So how will we make sure it's null? We're going to make sure it's null by having the pi dot q is equal to 0, pj dot q is equal to 0, and q squared equals 0. Okay? So in other words, and this is forced on us by demanding that p and ij squared of z stay equal to 0 for all z. Right? So we have to have whatever it is, that pi dot q is 0, and pj dot q is 0, and q squared equals 0. OK, you can try to do this in any number of dimensions. The idea of BCFW is valid in any number of dimensions. It's going to be especially nice in 4 dimensions, as we'll see. I mean, not especially, just particularly simple to work with, just because 4 dimension is simple. There's something you have to do with polarization vectors as well. But since we're not going to use the polarization in general dimensions, since we're not going to use the polarization vector language, I won't talk about it here. Oh, I forgot to have the references. Anyway, I'll mention the references at the very end of the lecture. Okay? OK, but now let's see what we have. Now we went from having a function of the momenta. now to have a function of the momenta as fixed, but we don't care about what they are, as a function now of z. Okay? And now we're going to do exactly the same game. We're going to first ask, where are the poles in z? Okay? Now, where are the poles in z? Remember, the only poles that the amplitude has are when a sum of a subset of the momenta go on shell, right? So in general, the only poles the amplitude has look like this. And we also know that they're supposed to factorize on the poles, okay? But what we have here is some sum of the momenta in some left set. Okay, so this thing has got to go, some PA, and some left set has got to go on shell. And when it does, we get this factorization. So now let's see how these could show up as poles as a function of z. Okay? So let's think of the two legs that I deformed, I and j. And let's imagine that the two legs are on the same side in one of these channels. Let's say they're like over here. Okay? Then this propagator, the thing that's going on shell, doesn't depend on z. All it knows is the sum of all these p's, which includes pi plus pj. And pi plus pj is z independent. Okay? So these factorization channels of the amplitude, these poles of the amplitude, do not show up as poles in z. The only thing that shows up in poles in z is when I is on one side and j is on the other. Okay? When I is on one side and j is on the other, what do we have? We used to have 1 over a sum of a bunch of p's plus p plus b plus, let's say, pi squared. That's what we had in the amplitude. And now this is going to get deformed because pi is getting shifted to pi plus zq. Okay, so this thing in the bottom is going to, if this whole thing was, let me call it p left, the whole thing is going to p left squared plus 2p left dot q z. And the z squared contribution is 0, right? Because q squared is 0. Okay, so you see every one of these factorization channels where j is on one side and I is on the other, there is a simple pole in z associated with it at this location. Okay? And therefore, there is a formula for the whole amplitude as a sum over those factorization channels because we know what the residue is, right? The residue is just a product of lower amplitudes. So let's write it down. This seems like too good to be true, but let's just write it down for a second. So naively, we say that m of the original amplitude, I can do it by the same argument, okay? But if I just follow exactly the same argument, I learned that m of p is equal to the sum over all the ways of breaking over all the factorization channels where I is on one side and j is on the other. The product of these lower point amplitudes at these deformed locations, so I'll call them hats, okay? Now multiplied by 1 over p left squared. Sorry. This over just p left squared. That 1 over p left squared is just the residue at z. Remember in our previous formula we had 1 over the zi, right? So this is exactly the analog of that formula. Okay? You just do precisely what we did before for the function of w. Now applied to this example, this is the formula we get. Where in this deformed amplitude, the z, so this is the sum over all the channels, the sum over all the channels where I is on one side and j on the other, and where the z for each thing is given by this formula. Z is equal to negative p left squared over 2p left dot q. Okay. This was too easy. there's one assumption that we needed to make here. What was that assumption? The assumption was the amplitude vanishes at infinity. If I say it more invariantly than vanishes at infinity, it's that I need to know the poles everywhere in the complex plane, including the pole at infinity. Okay, so there's you change variables from z to 1 over w. There's a pole at w equals 0 as z goes to infinity, right? So I need to know all the poles. All I know from factorization are the poles at these finite locations. A priori, I have no idea what the pole at infinity is. Okay? And so for this to work, it's crucial that m of z goes to 0 as z goes to infinity. Now, does that seem plausible? Let's do some very simple examples. Try for phi cube theory, right? Just at 4 points. Take phi cube theory at 4 points. Is it true? It's false. M of 0 goes to a constant as z goes to infinity, even at 4 points. Okay? And it's very easy to see because there's always one diagram where I and j are together, right? And in that diagram, there's no z anywhere as you go to infinity. That pole goes to a constant. It's false. Okay? So phi 4, phi cube, simple scalar theory, the statement is false. What about Yang-Mills theory? Well, you see, the limit we're taking is a high energy limit. You can think about this limit where I take the particles I and j, and I'm giving them larger and larger momenta. So there's a limit where sort of I is going to j is like an incredibly hard momentum blasting through a soft background of all the rest of the particles. Okay? And you can ask, do we have any intuition for what the amplitude looks like in this particular funny limit where q has to satisfy these properties? But for instance, if you check diagram by diagram in Feynman diagrams for Yang-Mills theory, there are momenta everywhere in the cubic vertices. And if you actually check, you would think that these things diverge as z goes to infinity. And diagram by diagram, they do diverge as z goes to infinity. Okay? I won't do this analysis for you. This is a thing in the reference I'll give you at the end of the lecture. Okay? But you can actually do this exercise of just seeing what the naive growth is. So the naive growth for m naive of z for phi cube theory is to go to a constant. That's the naive growth, and it's correct. The naive behavior for Yang-Mills, diagram by diagram, depends on the helicities of the particles. So maybe before doing that, before getting to the growth, let me tell you how we actually do this in 4 dimensions. More concretely, so all we need to do is we need to find a q. So we need to find a q such that q squared equals 0, and q dot pi is 0, and q dot pj is 0. And you see there are two choices that are just related by conjugation. For q squared to be 0, it should be some, I don't know, chi tilde rho, where these are 2 spinor helicity variables, right? So this is the most general null vector that I could write down. And then in order for this to be 0 when dotted into I and dotted into j, then either rho should be parallel to the lambda of I, and chi should be proportional to the lambda tilde of j, or the other way around. Okay, so there are 2 choices for what q could be. Q could either be lambda I, lambda tilde j, or lambda tilde I, lambda j. Okay, those are the 2 possible choices for q as a 4 vector. Okay? And so the way we conventionally then talk about this shift, let me leave this formula up, is that lambda tilde I goes to lambda tilde I plus z lambda tilde j. And so you deform the lambda tilde for I and the lambda for particle j. Okay, so that's what the that's what this deformation is at the level of the spin helicity variables. And of course, you can see, as we should, that lambda tilde I plus lambda tilde j, lambda j, pi plus pj goes to itself, okay, with no z. Right? So that's exactly what we saw before. Okay, so this is the shift that we're talking about now. And so you see that when you do this shift, we're treating the lambda tildes differently than the lambdas. And so the behavior of the amplitude as z goes to infinity could depend on the helicities of the particles that we're talking about. OK, so I will not go through this analysis. This is what was done in the paper I'll give you in the references. But I hope you can sort of, I hope you can believe me just from the fact that, there are momenta in all the Feynman rules that Feynman diagram by Feynman diagram, we have the following behavior. This is for Yang-Mills now. That if I look at the amplitudes for the helicity configurations minus, plus, minus, minus, and plus, plus, and plus, minus, that they could grow as fast as z, z squared, or even z cubed. Again, this is diagram by diagram. If I look at it in gravity, it's much worse, because now there are two momenta, right? So as I go to higher and higher n, now it's just explosive. As I go to larger and larger n, and naively diagram by diagram, in fact, you get z to the n minus 1. It grows with the number of particles, z to the n plus 1, and z to the n plus 3. So that's the naive behavior. OK? No. This is just diagram by diagram. This is all tree level. But we just say you pick a generic Feynman diagram. There are lots of momenta everywhere. And as you scale to high energies, they're all exploding. OK, so you look at phi cube theory, doesn't work. The amplitude goes to a constant, both naively and actually. OK? Now, Yang-Mills, you've got to add up a lot of diagrams. But naively, it's hopeless. None of them go to 0. Gravity is super hopeless. They're blowing up like crazy. OK? But here is where the magic happens. Our first magic is the actual answer. The actual answer, after you sum all Feynman diagrams, turns out to be the following. So that's the naive answer. The actual answer is that this is actually 1 over z. 1 over z for Yang-Mills. And funnily enough, plus minus is still z cubed. OK? And what about for gravity? These things that we're blowing up with more and more n, it's actually even better. It's 1 over z squared. 1 over z squared, and z to the 6th. OK? Now, this is remarkable. And there is a kind of a somewhat indirect argument. It's not a very complicated argument that I'll give in this reference at the end of the talk that establishes this using background field method ideas and clever gauge fixings and quite some work to try to show that this is true. Okay? But this is not something that's captured diagram by a diagram. Now, from a more modern point of view, we actually understand the origin of this magic, or we can at least relate it to other magical things. For example, the fact that these amplitudes die as you go to z goes to infinity, don't worry about that z cubed. This is what we're going to exploit in a second. And when we do things supersymmetrically, at the end of the class, everything is going to vanish at infinity. Okay, I will explain all of that. But yeah. Oh, this is whether the particles I and j have, that you're deforming have helicity plus minus, the minus minus or plus plus, or oh, sorry, minus plus. Sorry, I did this wrong. This was minus plus, and this is plus minus. Okay, so this is the helicities of the particle, right? So when we do this BCFW deformation, we're deforming two particles, I and j, and the behavior of the amplitude depends on the helicities of particles I and j. So under this shift. Because the shift that we do, remember we saw that there are two possible choices we could have for Q. Okay? It could be lambda I, lambda tilde j, or the other way around. I'm just choosing one of them here. Okay? I'm choosing one of them, and so I'm deforming lambda tilde for particle I and lambda for particle j. You could do the other way around too, and then you flip all the helicities around. Okay? All right, now let's just do a quick sanity check on these formulas, just so we see. Oh, sorry, but let me finish saying that in the case of Yang-Mills, we understand the origin. A deeper reason for this is that actually the Yang-Mills amplitudes have a hidden symmetry. The hidden symmetry of dual conformal invariance. Okay, now this is a remarkable thing. We'll be talking a lot more about dual conformal invariance and the Yangian symmetry and so on. But this is a hidden conformal symmetry that Yang-Mills enjoys, not just in 4 dimensions, but in any number of dimensions, at least at the tree level. It's very interesting that there's an obvious symmetry of theories of massless particles that we only have in 4 dimensions for Yang-Mills, but there's a hidden symmetry, a hidden conformal symmetry that's actually totally general in any number of dimensions. And it's this hidden symmetry that guarantees the absence of these poles at infinity for Yang-Mills. And then there's various relations between Yang-Mills and gravity amplitudes. We see here that the gravitational behavior is the square of the Yang-Mills behavior. That actually tells you that, that the magic about Yang-Mills, the hidden magic about the Yang-Mills amplitudes actually ports and gets augmented, gets squared when you go to a gravitational one. In fact, gravity is much, much, much more than Yang-Mills squared. But part of it is that it's like Yang-Mills squared. And so the magic that you see in Yang-Mills is reflected in the gravity. Okay? Yeah. Not true. That's right. Exactly. That's right. That's right. If we start adding, well, not dramatic ones that I remember. No, naively everything is broken. Okay, so this is, but of course, if we add higher dimension operators in the very special way that string theory tells us to add higher dimension operators, it's another story again. Okay, and so I think that but in any case, we're really imagining things just in the two derivative approximation, ordinary Yang-Mills theory. Yes. Nope. No. I mean, this is just for pure glue. It's true even for a pure glue, right? So pure glue is asymptotic. It doesn't matter how much matter you have. No. It's a very, very generic thing. It has very little. It's a tree level statement. It's not a one loop statement. Okay. So so this is what this fact is. Again, here's the irony. I want to stress it here because you have to get used to this in this business. You might think, oh, you want to learn about amplitudes. Let's start with the simplest example, like phi cube theory or phi to the 4th theory. We'll practice with that. And then we'll learn about QED. And then we'll do Yang-Mills. And then we'll do gravity. But that's kind of backwards. The reason you think phi cubed is simple is because it looks simplest from the point of view of the Lagrangian. But in many ways, it has the most complicated amplitudes. Okay? And the simpler amplitudes with more properties are for the theories with more spin, whose Lagrangian description looks very complicated, or more complicated. Okay? So BCFW does not work for phi cube theory, because nothing magical happens there, but something magical happens in Yang-Mills, and something even more magical happens in gravity. Yes. Yes. No, as I said, you don't strictly need it to 0. You just need the pole at infinity to vanish. Okay. Yeah. Yes. No, it's not good enough. That's right. Yeah. So there's a P. Yeah, that's right. It's not good enough. Yeah. There's no BCF. There's no analog of BCFW for phi cube theory. I should have put that on your problem set actually. Anyway, that's another nice problem. So one thing you could do is say, forget about all this. I gave you a formula. So now let's go back, right? So let's say I ignored this. I said, look, here's the beautiful formula. Let's just look at this formula. Why can't they just declare this is the answer, right? What does this answer make obvious? Let's just think about this for a second. Let's say I say, you see, this is a beautiful recursive formula for a higher point function in terms of higher point amplitude in terms of lower point ones. We're going to be computing a bunch of them in a moment. But let me first make a few general comments, okay? Remember, we have to check that the poles of this thing factorize correctly. So which one of the poles are obvious? Just the ones we put in, right? So this makes blindingly obvious that if I take the sum of these momenta and have it go on shell, well, puck, that's going to blow up. And on that pole, I'm factorizing to the product of two guys. Okay? So I've made exactly the poles where I and j are on opposite sides manifest. But now here's a miracle. Those are the only channels I'm summing over. There are no channels that have I and j together. But there are all those poles sitting there, right? So that has to somehow magically come out of the answer. And we're going to see that coming out of the answer is that the other poles are actually sitting inside here. And we don't have to separately introduce channels for all of them. OK, now, we saw that already. This basic phenomenon we saw when we were doing things more responsibly by looking at the consistent factorization of amplitudes. We saw the phenomenon that the pole in the S channel, the residue in the S channel, had a pole in the T channel, so that when you nailed the result in the S channel, whether you liked it or not, there was a pole in the T channel, which was actually the correct answer for the consistent theories. Okay, so we saw a little hint of that possibility already in our responsible investigations of 4-point factorization. Okay, but now we see that the behavior as z goes to infinity is actually this good magical behavior as z goes to infinity is porting that to amplitudes at all n. Let's just do a very quick sanity check. If I look at this Parke-Taylor amplitude, let's just see that some of the things that we said are true. So let's look at this over 1, 2, 2, 3, 3, 4, 4, 1. Okay, let's say I'm doing the BCFW shift, I don't know, on lambda on 4. Okay, so I'm going to do lambda tilde 4 goes to lambda tilde 4 plus z lambda tilde 1, and lambda 1 goes to lambda 1 minus z lambda 4. Okay? So what does this look like? Well, fortunately, it doesn't depend on lambda tilde at all. Okay? So all that I'm getting is this shift on lambda 1 goes to lambda 1 plus lambda 4. That 4, 1 is unaffected. But this 1, 2 goes to 1, 2 minus z 1, 4. And indeed, as z goes to infinity, it goes like 1 over z. Okay? So that's what I promised. And it's supposed to go like 1 over z. On the other hand, let's do one of the bad ones. I'm supposed to do, if, for example, I shifted plus minus is supposed to be bad. So let's say, sorry? I'm shifting lambda 1 goes to lambda 1 minus z lambda 4. Okay, so 1, 2 goes to 1, 2 minus z, minus z 2, 4. Sorry about that. Sorry about that. Oh, sorry, we do. And that's because I did exactly the incorrect shift. Sorry. Excellent. Thank you. We do. So let's do this properly. Okay, so if I do this shift, I get 1, 2 minus z 4, 2 downstairs, blah, blah, blah. Upstairs, I get 1, 3 minus z 4, 3 to the 4th. So the whole thing goes like z cubed. Okay, and that's good because I did the illegal shift. I did the plus minus shift. Okay, I shifted lambda tilde 4 and lambda 1. That's why Professor Strominger has got to sit in on this class, so I don't lie to you. Right? So let's say we do the other way around, though. Right? If I shifted, anyway, if I do another one of the shifts, I just get the z downstairs, and it goes like 1 over z. Okay. All right. So, any questions about these generalities so far? Is it clear what's remarkable about this formula, right? Summing only over some of the channels is giving us the answer with singularities in all channels, and this is possible because of this remarkable behavior as z goes to infinity. That fact, if you like, I said earlier that there's all sorts of cancellations in Feynman diagrams, blah, blah, blah. This sharper fact about the amplitude vanishing as z goes to infinity encapsulates all those statements into one clean fact, which is the origin of a lot of the magic. We'll see much, much more of it later. And again, this is the first hint of the underlying dual conformal symmetry and other things we're going to see more of. Yes?
But there's no other way to know that cancellations occur than actually compute summing the diagram?
No. Well, in this paper that I'll give the reference to at the end, there was a way of doing it. It's not a very complicated argument, but it's an argument. It's not a very simple argument. You don't sum all the diagrams, but you find some way of effectively doing that. So what you do is you look at this amplitude in the large z limit by setting it up as the question of a hard particle blasting through a soft background and setting up a consistent expansion in powers of 1 over the hardness of the scattering. Okay? And when you do that and gauge fix in some clever way and do things correctly, you can discover this 1 over z behavior. Okay? But it's not super obvious, and it's not what you get from ordinary Feynman diagrams. You know, so it's another way of doing the gauge fixing. It's anyway, it's a background field method type argument. And that, to this day, if you want a direct argument why it's true, that's the sort of best argument that we have for why it's true. Okay, so again, yeah. Sorry? Well, we have to be careful what we mean by soft and high energy, because string theory is soft and high energy in very particular directions. And so, yeah, so there are some directions you can go in where it's true in any channel, and people have used that to come up with sort of interesting recursive formulas for string amplitudes. And we might talk about that when we get to string amplitudes towards the end of the course. Yes. No, it's not. I mean, it's not bad. It's like it's in this funny direction that you normally don't think of going in. Okay, so there's this funny. This corresponds to, in Minkowski space again. Q is a complex direction. It's not for real Lorentzian momenta, anything like that. Okay, but that's just what you get. That's what you get term by term in diagrams. All right. So now we're just going to. Everything okay? All right. Now we're actually going to compute some of these guys. Okay. So let's compute some, and so as I say, we're now more proactive. So let's. Oh, sorry. But what I was going to say is that, and this is an exercise that you should do. Let's say you ignored all of this and you say, screw you. That's the answer. I'm going to just take it. I'm going to use it for phi cube theory. What's going to happen? You'll get an amplitude. Well, you should do it. Okay? And you'll find either you're missing poles you're supposed to have, or you'll have weirdo poles. We're going to see some weirdo poles in a moment that you have term by term. You're going to find an object that sucks. Okay? You can build it, but you'll find an object that sucks. It'll either not have the poles it's supposed to have or have poles it's not supposed to have. Okay? And so you can check. And that's something that we will later do, except we won't do it in this analytic way. Starting in about in 2 or 3 lectures, when we start talking about on-shell diagrams and the Grassmannian and so on, we're going to manipulate all these expressions with pictures, so that everything is just going to be pictorial, and all the identities they satisfy will become obvious, and so on. So I'm going to defer the more conceptual ways of explaining some of the patterns that we're going to see today, just by explicit calculation. I'm going to defer that to when we have pictures, so that we can just see them obviously. Okay? But anyway, if you did it for phi cubed or some other dumb theory that doesn't work for, you'll be rewarded by getting garbage that doesn't have the correct poles and doesn't factorize properly. All right. Well, let's do something that's not garbage. Let's take the Parke-Taylor amplitude. So let's start with Parke-Taylor. So let's first get an idea of what the BCFW diagrams are. Let me choose some 4-point process. Let's say we choose these helicities, 4 plus 1 minus, 4 minus 1 plus 2 minus 3 plus. And so I'm going to deform 4 and 1. Okay, so 4 and 1 are going to be the guys I'm going to deform. I'm going to put hats on them. So I have lambda tilde 4 hat is lambda tilde 4 plus z lambda tilde 1, and lambda 1 hat is lambda 1 minus z lambda 4. Okay? And so remember, what we're supposed to do is look at the channels where I and j are on opposite sides. Well, fortunately, there's only one of them in this case. The channels where I and j are on opposite sides is just this one, just with the 3-particle amplitude on both sides. Okay, so I have 3 plus 4 minus, some intermediate, and then 1 plus 2 minus. Okay, just one diagram. Now, before actually computing it, let's just look at what the pictures look like, let's say at 5 points. So at 5 points, let's say I have 5 minus, 1 plus, 2 plus, just choosing some random helicities, 3 minus, 4 plus. Remember, we're computing these amplitudes with 2 negative helicity particles. Now there are in principle 2 channels that we can have where 5 and 1 are on opposite sides. One of them looks like this, 4-particle amplitude on one side, like 5 minus 1 plus, 2 plus, 3 minus 4 plus. And I have the other one. Where it's 4 plus, 5 minus, 1 plus, 2 plus, 3 minus. Okay, so these are the two factorization channels that could show up, right? Where 5 and 1 are on opposite sides. So I'm deforming 5 and 1 here. Okay, but now let's look at these. In order for this amplitude to be non-zero, right? This is plus plus. So this guy would have to be a minus, and that guy would have to be a plus. Okay? And therefore, this minus plus plus is an amplitude where all the lambdas are parallel to each other. Okay? Can I reach that? Well, yes, I can, because lambda is exactly the thing that I deformed. Sorry, I'm deforming. So in this case, lambda 1 goes to lambda 1 minus z lambda 5. Lambda tilde 5 goes to lambda tilde 5 plus z lambda tilde 1. Okay? So this one is good. We'll get something from that. But we will not get something from this guy. So what's the analog over here? For this amplitude to be, now on this side, for this amplitude to be non-zero, this had better be minus. So that had better be plus. This is again a plus plus minus amplitude. Again, for this thing to be non-vanishing, all of the lambdas have to be parallel. But I'm not touching lambda 5. I'm just deforming lambda tilde 5. Okay? So I cannot reach, as a function of z, I do not have the pole where lambda tilde 5 becomes parallel to lambda tilde 4. Lambda tilde 5 is whatever it was to begin with. Okay, so this one does not contribute, and this is the only diagram which does. Okay, and this is a feature of the amplitudes of two negative helicity particles. By the way, the name for the amplitudes of two negative helicity particles is MHV amplitudes, maximally helicity violating amplitudes. Don't ask me for the historical reason for that name. But it's true for any amplitude with 2 minus, for any MHV, 2 minus amps, there's only one BCFW diagram, and that contributes. And if I'm deforming lambda tilde n goes to lambda tilde n plus z lambda tilde 1, and lambda 1 goes to lambda 1 minus z lambda n, then that diagram looks like this. N is on one side, and then on the other side, I just have just this 3 particle amplitude, just with one. Let's say n has any helicity, it doesn't matter. 1 has helicity plus, though, and 2 can have any helicity you like. Now, notice that what am I allowed to shift? I should have said this up there. I don't have to be careful about who I shift so long as j is plus, because anything plus goes to 0 as I go to infinity. Okay? So I don't care what the helicity of n is. I don't care about anyone else's helicity. This is the only diagram that contributes wherever I and j are. Maybe 2 is negative, maybe 2 is positive. It doesn't matter. Furthermore, it's very easy to see, because this amplitude has to have all of the lambdas parallel to each other, this amplitude, whatever it is, has to be one of the plus plus minus variety, right? And that means that whatever this helicity h is for 2 here, the helicity of this internal line has got to be the negative of that, because I have to have 2 pluses and a minus. Okay? So let's say 2 was minus, this would have to be plus. Let's say 2 was plus, this would have to be minus. And so therefore, this guy over here also has helicity h. Right? So we have to learn to compute that diagram. Okay? We compute that diagram, and then we divide by 1 over p left squared. In this case, p left squared is just p1 plus p2 squared. It's very simple. Okay? Now, I'm going to actually do this computation, not assuming this is a lower Parke-Taylor amplitude, a lower MHV amplitude. I'm going to do the calculation for this piece of a BCFW calculation, no matter who is in here, no matter what amplitude is in here, because it happens that this has a very simple and nice formula in general. It's useful to know. Not all BCFW formulas are as simple as this, but this is so simple that we might as well do it in general, just so you see what the general structure is a little bit more easily. Okay, so I'm going to try to work out what this is, whatever function I have here, whatever amplitude I have there. Okay. no matter how many minuses and pluses it has. OK, let me just pause for a second. So we're actually doing, I'm going through every step of this computation. OK, so stop me if anything doesn't make sense. OK? So far, so good? Yes. Sorry? We have to have 2 pluses on the, sorry, over here. Well, if we're literally doing MHV, then, well, maybe H is minus, in which case it would only be 1 minus over here. If H is plus, there would have to be 2 minuses over here. But for the moment, I'm just shoving anything over here and just working out what this product is. OK, so the first thing to do is to work out what Z is here. So remember, I have lambda hat 1 is lambda 1 minus Z lambda n. And what am I trying to do? I'm trying to bring it to a configuration where 1 hat 2 is equal to 0. Right? I want to make 1 parallel to 2. So I have to bring it to a configuration where 1 hat 2 equals 0. So I can use that to solve for Z. OK, so from here, 1 hat 2 equals 1, 2 minus Z n2. And therefore, Z is equal to n2 over 1, 2. All right? And so now let's work out who all the other variables are here, right? There's some intermediate momentum we got to work out. There's the lambda tilde for n that we have to work out. And actually, there's lambda 1 to work out itself. So let's work out what is actually lambda 1 hat. Lambda 1 hat is, well, let's just shove in, is lambda 1. Let me put it under a common denominator. Oh, sorry. I did this backwards. Very important. OK. Is lambda 1 n2 minus lambda n 1, 2 over n2. OK, and now there's a little identity, which is the first exercise on your problem set. There's a totally trivial fact about 3 two-dimensional vectors. So you have 3 two-dimensional vectors, lambda 1, lambda 2, lambda 3. They satisfy a linear relation because I can express any one of them as a linear combination of the other 2. And this relation, you can remember it in many ways. The kind of universal way to remember is that you just take the alternating sum, taking one of them out of the bracket. OK, so that's the linear relationship between the 3 two-dimensional vectors. And so that tells us that this combination, lambda 1 n2 minus lambda n 1, 2, is actually equal to lambda 2 n1 over n2. OK, that's very good because we knew that lambda hat 1 had to be proportional to lambda 2. And here it is, right? It's proportional to lambda 2, and here's the constant of proportionality. OK? In fact, and you should start getting used to this when you're playing around, you don't have to always do these manipulations. We could have guessed that very easily. How could we guess it? We know that lambda hat 1 has got to be proportional to lambda 2, but we can't just write down lambda hat 1 equals lambda 2. They have the different little group weights. So you have to multiply it by something that converts a little group weight of 2 into 1. That's why you multiply by n1 over n2. Okay, and n1 over n2 just converts the little group weight of 2 into 1. OK? So we're starting to learn what this kinematics is on this channel. Let me record what we know so far. So we know that lambda 1 hat, we know lambda 1 hat is equal to n1 over n2 lambda 2. OK, now let's, yes? No. So we needed the amplitude as z goes to infinity to die in order to be able to set up this Cauchy formula. Okay? So now what we're doing is summing over all the poles in z. Okay? This is z at the pole. That's right, exactly. What I've done, yeah, thank you. What I've done is deformed, and I want to hit this pole. I'm hitting the pole where 1, 2 is equal to 0. 1 hat 2 equals 0. I'm just working out what that is in z. I worked out what that is in z and what lambda is there. So now let's work out what is lambda tilde. So remember, lambda tilde n hat is lambda tilde n plus z lambda tilde 1. So we know what the formula is for z. So this is lambda tilde n plus n2 over 1, 2 lambda. What did I do? Ah, I did it again. Plus 1, 2 over n2 lambda tilde 1, which is, this is also a nice formula. If I put it under a common denominator, this looks like Pn plus P1 times lambda 2. Okay? See, this is lambda tilde n times 2, lambda tilde 1, lambda 1 times 2. Okay, so this is Pn plus P1 times 2 over n2. Is this notation clear? Sometimes I'll put these, the thing in the, okay. So this whole thing is going to have an alpha dot index, and that's why I'm writing it like this. Okay, so let's record this over here. Lambda tilde n hat is Pn plus P1 2 over n2. And now let's finally work out what the lambda and the lambda tilde is for the intermediate guy. All right. Now, as we saw last time, I'm free for the intermediate guy. I don't know what the overall weight is for lambda and lambda tilde. I do know that lambda intermediate, from this side, lambda intermediate has got to be parallel to lambda 2, has got to be parallel to lambda 1. So I'm free to choose lambda intermediate itself is lambda 2, let's say. And then I have to solve for lambda tilde intermediate by momentum conservation on the right, which I can write as an overall lambda 2. There's an overall lambda 2, an overall lambda 2. There is lambda 2 tilde itself, that's P2. There's there's n1 over n2 lambda tilde 1, and there's lambda tilde for the intermediate. Okay? So that lets me solve. So this has to equal 0. So from here I learn, well, I just solve for lambda tilde. And from here I learn, let me write down the result here, that lambda tilde intermediate is equal to, also a pretty formula, P1 plus P2 times n over 2n. All right, so now we're done with all the kinematics. We know what lambda and lambda tilde are on the left and the right. And therefore, this particular term in BCFW, so 1 over P1 plus P2 squared times whoever this is, n, times 1 plus whoever this is, hat, okay? This is equal to 1 over P1 plus P2 squared is 1 over angle bracket, square bracket, 1, 2. On this side, I have, depending on the helicity of 2, I have either 1i cubed over 1, 2 I2, or 1, 2 cubed over I1, I2, depending on which one of these guys is plus. Okay? Well, we'll come back to that factor in a second. That factor is going to be trivial. But the really interesting thing is this object on the left. Whatever this amplitude is on the left, I have some m left evaluated on an amplitude m left I, 3, 4, and so on. So lambda I will be lambda 2. Lambda tilde I will be the formula that we have, P1 plus P2n over 2n. Okay, so much for I. Then lambda 3 is unaffected. Lambda 4 is unaffected until the end. Lambda n is unaffected, and lambda tilde n is equal to the formula we have there, Pn plus P1 times 2 over n2. Okay? And now let's just do our final little exercise to work out what this factor is. Well, that factor is extremely simple. Just from the formula, we don't even have to take this formula for lambda tilde I. We just saw it because of where it came from. We had lambda tilde 2. We saw the same manipulation last time. Plus n1 over n2, lambda tilde 1 plus lambda tilde I equals 0. So that tells us that 1I, that tells us that I1 is just the same as 1, 2, and I2 is the same as n1 over n2 times 1, 2. And so you see, whichever one of these things you shove in, this expression is always the same. It's given by angle bracket 1, 2 multiplied by n1 over n2. All right, so let me summarize the final answer now. So this particular BCFW diagram is equal to the contribution I get from BCFW, so 1 over P1 plus P2 squared times this is equal to the following lovely formula. Whatever the left amplitude is, let me write it all out again, at lambda I equals lambda 2. Lambda tilde I equals P1 plus P2 n over 2n. Everyone unaffected. And then lambda n and lambda tilde n equals Pn plus P1 2 over n2 multiplied by, and everything else just turns into this lovely factor of n2 over n1, 1, 2. Oh, God damn it. All day long I've been inverting this. Okay. Now, I've written this in this generality for a variety of reasons because we actually are going to learn a few amusing things. There's an amusing interpretation of this formula, which is interesting, and which we'll be seeing more things like this. What happens as the momentum of particle 1 goes to 0 in this formula? So let's say P1 goes to 0. See, as P1 goes to 0, what does this lambda tilde I turn into? P1 goes to 0. This is just P2n over 2n. So lambda tilde I just becomes lambda tilde 2. So lambda I just basically becomes 2. What about lambda tilde n? Well, as P1 goes to 0, lambda tilde n is undeformed. Okay? So in the limit, as P1 goes to 0, this whole thing is just as if I had this amplitude with 2 sitting there. Right? So that also tells us something, that in the limit as the momentum of 1 goes to 0, there is a singularity in the amplitude which is sitting here, right? A 1 over n1, 1, 2. So this is the universal behavior of the amplitude as the momentum of the gluon 1 goes to 0. It's extremely beautiful. As the momentum of gluon 1 goes to 0, now this is the color-ordered amplitude. So 1 is now stuck between 2 and n. Okay, so it has 2 neighbors. But as the momentum of 1 goes to 0, what I get is the amplitude without particle 1, okay, multiplied by this factor, n2 over n1, 1, 2, which is the world's simplest way of just making sure that I have helicity weight in particle 1 and nothing else. Right? I got rid of the weight in n and 2. there's 2 1s downstairs, which correctly matches the fact that 1 has helicity plus. Okay? So this is a universal behavior for Yang-Mills amplitudes. In the limit, as a positive helicity gluon goes to 0, if it's emitted between its 2 neighbors, you just get the lower amplitude multiplied by this simple factor that encapsulates the pole that you're supposed to have as the momentum of 1 goes to 0. Okay? And in fact, you can convince yourself that we've actually derived the soft limit from BCFW, because the only term in all the possible other BCFW terms you could have, the only term that has this pole as particle 1 goes to 0 is this diagram. Okay, so we've actually done it. We've actually proven that this is the universal behavior of the gluon amplitudes. But you can also see this formula kind of has a cool interpretation. This piece of BCFW, and so we're getting sort of very early hints of the kind of structures we're going to see coming up later. I can think of this as some amplitude 2, 3 up to n, and this piece of BCFW is like I figured out some way of adding particle 1 in between 2 and n. Okay? It's like an inverse soft factor, right? I figured out how to deform the lower amplitude. So now I have to add the momentum of particle 1, so I can't leave things alone. And so I don't leave them alone. I deform 1, and I deform 2, which is I here, and I deform n in this very beautiful and simple way to absorb the momentum of 1 that I added. And I exactly tack on this soft factor, which is guaranteeing that if I take the soft limit of the particle that I just added, it'll be correct. Okay, so that's an interpretation. This is not a very super general thing, but it just shows that there are these, we're already seeing some little combinatorial-esque interpretations of these operations that we're going to see in much greater, fancier generality when we see these things in pictures. Okay? When we draw these diagrams in pictures, you will see why this is called an inverse soft factor. That literally is going to look like taking 1 and shoving it in between 2 and n, okay? Which in a way that we don't see now, we see a little bit more analytically. All right, so that's it. And so we're now going to compute this term in BCFW. We're going to go back to our Parke-Taylor formula. Any questions? Yes? Yes, absolutely, which you see here, right? So we see that the only term is the one where it's on this external guy. It looks like 1 is being emitted off the line too. Okay? Except we're not doing with Feynman diagrams. Okay? These are all totally on-shelf things. Okay. So let's go back to Parke-Taylor. Let's do our first simple example. So let's look at, so now we're just going to apply this formula over and over again. So let's look at 3 plus, 4 minus, 1 plus, 2 minus. Okay, so what is this term? Well, we just have to apply our general formulas. And life is especially simple because the only thing we modify on the left are the lambda tildes. Well, thankfully, nothing depends on lambda tilde on the left. So remember, I was just set to 2 in this formula. So on the left, I get I is 2. On the left, I just get 2, 4 cubed over 2, 3, 3, 4. Right? Because this has to be minus, that has to be plus. And I'm supposed to multiply by this factor n2 over n1, 1, 4, which is 4, 2 over 4, 1, 1, 2. So up to signs, this is exactly 2, 4 to the 4th over 1, 2, 2, 3, 3, 4, 4, 1. Okay, that's the Parke-Taylor formula. Okay, and again, we've said it already on general, but it's remarkable. This one channel is capturing the other channel. And we saw that, as I said, in our more systematic bottom-up construction as well. But anyway, we're seeing it now in BCFW. But now the remarkable thing is that this is true for all the MHV amplitudes, because they all just had a single BCFW term, which was the thing that we just computed. So for example, let's look at the case where it's I and J are minus, or A and B are minus, A minus B minus N 1, 2. then it's utterly trivial because this diagram is just given by, so remember I would be given, it would be 2 now. So this would be AB to the 4th recursively, the lower amplitude, over I3. So 2, 3, this would be 3. 3, 4, blah, 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 blah. And then Ni, or N2, and then it's multiplied by that factor, multiplied by N2 over N1, 1, 2. And you see the only problem with this amplitude is that everything was correct, but it was linking up N and 2. And that's exactly what this is doing. It's erasing N2 and replacing it by N1, 1, 2, so that this is indeed AB to the 4th over 1, 2, 2, 3, up to N1. OK? So we've derived the Parke-Taylor formula from BCFW. Okay, and this was a case where it was very simple because there's only a single term in BCFW. Now let's move on to the thing that's really interesting, our first really juicy amplitude. This is a 6-point amplitude. And of course, if 2 or minus, we know the answer. So we want an amplitude where 3 are minus and 3 are plus. Okay? So I'm going to look at the amplitude 1 plus 2 minus 3 plus 4 minus 5 plus 6 minus, the scariest one. Okay, where the helicities are totally mixed up. Now how many BCFW diagrams are there? Here, there are 3 of them. Again, I have to find. I'm again going to shift 6 and 1, and so I have to draw all the possible factorization channels with 6 on one side and 1 on the other. Okay, so one of them is the kind that we've just talked about extensively. So that's one diagram, 1 plus 2 minus, 3 plus 4 minus, 5 plus 6 minus. That's one. But I also have one where there's, looks like that. 1 plus 2 minus, 3 plus 4 minus, 5 plus 6 minus, and another one that looks like this except on the other side. OK, and now you can easily convince yourself none of these diagrams vanish. OK, just they're all non-zero. All right, and they look different, right? I mean, and they're not even obviously symmetrically related again because we're breaking the symmetry between 6 and 1 by deforming 6 on one, by lambda tilde on one side, lambda on the other, and so on. So now you're going to compute this on your problem set, right? But I'm going to tell you the answer, and we're going to compute this piece because we've learned how to compute that anyway in general, right? So let's just compute that term, which is one of a special case of our general things, and let's see what we get. It's already going to be very instructive. So if I look at this first term, so let me call this term 1. Right, so what is term 1? Let me draw it again over here. So this is I on this side should be minus, and this side the I is plus. OK? So the amplitude on the left, notice, has 2 pluses and 3 minuses. OK? So that's good. We know that one. That's just the opposite set of brackets compared to the normal Parke-Taylor amplitude. So let's write down the guy on the left. This is 3, 5 to the 4th over, and this is all hatted, right? Over, well, I3, 3, 4, all the other kind of bracket, 4, 5, 5 6 hat and 6 hat I. And I have to multiply by our famous n2 over n1 1 2 factor, which in this case is just 6 2 with the other kind of bracket over 6 1 1 2. OK? So now all we have to do is shove in who is I and who is lambda tilde 6 hat. And we know what those formulas are. We know the general formula. So we know that 6 tilde hat is equal to P6 plus P1 2 over 6 2. And I tilde hat is P1 plus P2 6 over 2 6. OK, so let's see what we're going to get. All right, well, first let's collect all. We're going to have a lot of 6 2s upstairs. So this I has a 6 2 downstairs. So does 6 hat. OK, so from all of these things, we're going to get an overall 6 2 to the 5th upstairs with that extra 6 2. So we have 3 5 to the 4th, 6 2 to the 5th. Now let's just patiently write everything down. So so first let me write down the simple thing. So I have 6 1 1 2, the other kind of bracket 3 4 4 5. Then I have the slightly more exciting things like this I3. So I3 looks like 6 P1 plus P2 3, and 5 6 looks like 5 P6 plus P1 2. And then maybe the most exciting one is the 6 hat I, which looks like 6 P1 plus P2, P1 plus P6, 2. So this looks like a little bit of a funny formula. But this is a lambda tilde-like object. This is a lambda tilde-like object. And I'm just contracting them. OK? All right. So let's just relax for a second. What kind of poles should we expect the amplitudes to have in general? Well, we're clearly going to have the poles that we put in by hand. That's fine. We're going to have the P1 plus P2 squared pole. But for instance, we should have the poles and this 6-particle amplitude is going to have poles when a sum of 3 momenta go on shell. Now, in the BCFW expansion, one of the terms looks like that, right? One of the terms that looks like 4 5 6 on one side and 1 2 3 on the other. That one is going to be there in one of the BCFW terms. But the other ones are not there. Like, what about P6 plus P1 plus P2? That's not there naively in one of the expansions or the other one. So they somehow have to be in here, right? So where is it? Well, it's actually in this term. So let's simplify this term a little bit. So this term is actually not so bad. P1 squared is 0. So let's just simplify this term. So P1 squared is 0. So this is 6 1. And on this side, I get P1 dot P6. So this will be bracket 1 6, the other one. And on the other side, I'll get 6 2. Then I have this term, which is 6 2. This bracket, which is 2 1. And then 1 2. And then finally, the P2 dot P6 is again 6 2. Square bracket 2 6 and 6 2. So I can factor out of this an overall 6 2, and then what's left is just P1 is P1 dot P6 plus P1 dot P2 plus P6 dot P2, which is otherwise known as the 6-2 times P1 plus P2 plus P6, P6 plus P1 plus P2, let me just write it like that, squared. Beautiful, right? So that's our pole. That's our pole in the other channel. Okay. Okay, so that eats up one of the 6-2, so let's write down the final answer. So term 1 is equal to 3/5 to the 4th, 6/2 to the 4th, over 6/1. 2. Oh, what am I doing? And there's 2 more funny poles. Okay? One of them I can write as, how do I like to, this is for a later convention. It's just purely a desire to write it in a particular way. Yeah, so let me write it as 5 P6 plus P1, 2, and another factor, which is 6 P1 plus P2, 3. Okay, and for the first time in this course, I try to copy some of my math friends who are so good at using multicolored chalk, chalk in many ways. I'm going to put a big, scary yellow thing around these guys. All right. Okay, so this is term 1. Okay, the full amplitude turns out to be the sum of 3 terms. And this is what you'll do on your problem set. It's not super obvious that what I'm about to say ends up being true. It will become super obvious when we manipulate the pictures in a few lectures. Okay, but the full amplitude ends up being just 1. So a 1 plus exactly the same expression where you just rotate all the indices by 2 plus exactly the same expression where you rotate all the indices by 4. So it's remarkable that the other BCFW terms end up being exactly the same expression, just rotating the indices over. Okay? It's not obvious that it should end up being that way, but again, it'll be trivial when we draw the pictures and see how all these things work graphically. You should do this exercise once in your life so you appreciate what we're going to get with all the pictures. Because when we play with pictures, all this stuff is just going to happen for free, but you'll see that it's actually buying you something. It's taking care of all this algebra for you. Okay? Now we've seen, but anyway, so the claim is the answer is all kinds of correct poles. It has all the correct poles. It has the obvious correct poles that had to be there that we put in. It has, in this sort of magical way, the poles from the other channels. Now we see, unlike in Parke-Taylor, an example of even one of the multi-particle poles that we have in the other channels. But now we see for the first time a novelty that we did not see with the Parke-Taylor example, because the answer is the sum of many pieces. Each piece also has these weird poles. Okay? These are called spurious poles. And they're spurious because they do not correspond in any way to a sum of a bunch of momenta squared. These are not poles that are allowed for amplitudes to have. They're illegal poles. In fact, I encourage you to just multiply it by its conjugate and massage it to see what kind of expression you get. Okay? You don't get something that looks like 1 over p squared. You get something roughly that looks like 1 over p squared q squared minus r squared t squared. Okay? Not things that look like 1 over p squared. So this is very striking. If you were to compute this 6 gluon amplitude any other way with Feynman diagrams, you're swimming in 1,000 pages of algebra. Okay? We get the answer as a sum of 3 terms. But what's remarkable is that the sum of 3 terms is expressed in a way that somehow does not care so much about space-time locality. It has some poles that are correct, and some poles that don't correspond to any ordinary local processes in space-time. Illegal things. Of course, those spurious poles magically cancel in the sum. Okay? You sum the three terms. Of course, the spurious poles are gone, but they magically cancel in the sum. And one thing you'll do on your problem set is just check that it's true. Not so easy to algebraically check that it's true. I encourage you to do that with Mathematica or Maple or Sage or whatever your favorite symbolic manipulation package is. Okay, but it's not so easy to symbolically verify that the spurious poles actually cancel. They cancel in pairs when you sum. Now, when you play with this a little bit more, you discover that, in fact, there is yet another way of running BCFW recursion. Instead of doing 6 and 1, you could shift everyone over, right? And that would give you a different expression. So you have a formula that looks like an expression that looks roughly like 1 plus 3 plus 5. There's another expression that looks like 2 plus 4 plus 6, another 3-term expression. And so there's a 6-term identity that's satisfied that says 1 plus 3 plus 5 equals 2 plus 4 plus 6. Okay? So these objects that the amplitude is built out of, these BCFW building blocks, they satisfy lots of remarkable identities between each other. They have all kinds of properties that are not so obvious. You start seeing them when you when you begin to compute them. Yes. Well, yeah. So that's so. Let me come to that in a second. So of course it would be yes, they cancel later, but somehow the final actual answer is more complicated looking when you combine everything together in one big common denominator. It's much more complicated looking this way of decomposing it into simpler parts. Okay? Now, all of these things are actually the very beginning indications of a picture that these amplitudes are actually the volume of something. They're the volume of something, and these pieces are taking that volume and cutting it up, triangulating it in different ways. And there are different ways of cutting it up. Each way of cutting it up has these interior facets that cancel in the sum. And so if someone handed you a complicated shape, yes, you'd say invariantly it's the volume of that shape, but you want to give a simple expression for it, you break it up into pieces. Okay? It's more than the simplicity of these expressions. Remember I told you that there ends up being a symmetry reason why the poles at infinity canceled. And we didn't have poles at infinity. And there's this hidden dual conformal symmetry. In fact, as we'll study, I didn't get the supersymmetry this time. We'll do it next time. But as we study these things, we'll discover that these BCFW terms are individually invariant under the dual conformal symmetry. In fact, they're individually invariant under this full Yangian symmetry of the n equals 4 of the maximally supersymmetric theory. So it's more than just that they're simple and the answer looks simple. These are the natural building blocks that expose all the symmetries. Okay? But this dual conformal symmetry, as the name implies, is a conformal symmetry in a dual spacetime to the original spacetime in which the gluons live. So that makes it even more clear that these things don't care so much about spacetime. They don't care about one spacetime or the other spacetime. They care about the symmetries. They don't care about having fealty to any one or other local description of the physics. So that's the kind of clue that we're going to start exploring more and more. But just to give you 2 minutes, an idea of the plan for the next few lectures, tomorrow we'll begin just with 15 minutes on maximal supersymmetry. It's extremely simple. And the really beautiful thing about supersymmetry, from this point of view, amongst other things, is that we never have to keep track of these stupid minus plus helicity indices anymore. Okay, when we have maximally supersymmetric theories, all helicities are unified into one multiplet. And so everything is done with no minuses and pluses anymore. So we have even smoother, simpler looking objects. Okay, and we will find supersymmetric amplitudes that begin at 3 points just with black and white vertices, telling you whether the lambdas are parallel or the lambda tildes are parallel, but with no information about helicities. And then what we're going to do is just start playing. Okay, so after doing some more computations, we're going to start playing, and we're going to see what happens when we take these building blocks and we glue them together. So for instance, we'll do something like this, and we'll wonder if that means something like a tree amplitude. We won't see that it's not a tree amplitude. Okay? Everything here is going to be on shell. So we're going to be playing pictures where everything is on shell. These are not Feynman diagrams. They're what you might call on shell diagrams. But then as we play some more, we'll discover that something like this computes a 4-point amplitude. And in fact, we'll discover that the entire story of BCFW recursion just corresponds to taking something on the left and the right and putting this little hat on top of it in terms of these pictures. And we'll find simple diagrammatic rules and equivalences between these pictures that sort of trivialize a lot of the computations that we're actually going to do. And step by step, we're going to see that this is actually exposing some auxiliary structure in a Grassmannian that's controlling controlling a lot of these things. And then anyway, there's a whole story after that. But after we do supersymmetry tomorrow, and actually before we start doing this playing, we're going to spend 1 or 2 lectures on a last bit of kinematics that we need to get under our belts. So the plan for the next 2.5 lectures is we'll do supersymmetry, we will do twistor space and momentum twistor space, and we'll spend an entire lecture on projective geometry. So we're going to have 1 lecture, we'll turn you all into expert projective geometers, so that when we start doing all kinds of fun games in projective space, you will know what you're doing. OK, thanks a lot.